Good morning. This is Michael Dong, and here is episode number 21 on HPLC operations, best practices, and standard operating procedures. Here is a summary of the next three videos, which include HPLC operation, maintenance, and troubleshooting. Those are topic for the next three episodes from 21 to 23. The first one, HPLC operation, are all the yellow ones, include all the module, standard operating procedure, qualitative and quantitative strategy. The next video would focus on HPLC maintenance and what the analysts in the lab can do, which are those labeled in green, which include safety and environmental concerns, mobile phase sample preparation, and HPLC maintenance, and what the laboratory analysts can actually do. The third one is on HPLC troubleshooting. Here is the agenda on today's video on HPLC operation, which are divided into three different segments. First one is the best practice on HPLC operation, including all the standard operating procedures or SOPs for the different major module, including the pump, columns, auto sampler, column oven, and UV detectors, and also including how to shut down your HPLC system properly. The second segment is guidelines for improving precision and sensitivity, a strategy to improve retention time and peak area precision, and how to increase method sensitivity with UV detection. The third one is on qualitative and quantitative strategies, including an overview on the analytical testing workflow, qualitative and quantitative strategy, and the best practice in CDS, which stands for chromatography data system data handling. These will be documented also in the book chapter number 7. This slide summarizes HPLC standard operating procedures. We start with, for most intensive purposes, placing the solvent line sinkers, including the frit or the filters inside the solvent reservoir. The solvent reservoir should be capped to prevent evaporation. For those using a needle wash basin, the solvent to use typically would be 50% methanol with water, and also including those for the needle wash and the seal wash. There are older systems would require dry prime and wet prime. Dry prime is needed if the pump are dry by withdrawing the solvent from opening the purge valve with a 10 ml syringe. Some of the modern system does not require this operation because there's an auto purge valve, and some pump actually can auto purge from a dry state. Wet prime are needed when changing solvent with older system and with most system, which is to operate it at very high flow rates, such as 3 to 4 mil, with the valve open for anywhere from 2 to 4 minutes. Most pumps have a built-in vacuum degasser, typically with 4 different lines. Very important, even though you're using line A and B, for most laboratory, only A and B are being used. C and D lines should also be filled with solvent so that the vacuum pump would not be just sucking air. So it should be filled with solvent. In general, the column should be rinsed with strong solvent first before any operation, and then equilibrate the column for 1 to 3 minutes until a stable baseline and a stable pressure are obtained. Generally, at the end of the sequence, we program the method to purge the column and shut down the pump, also the oven and the lamp, automatically after the sample sequence is completed. There are also some solvent for some specialized operation. First, if there's buffers in the line, should be flushed out with 10% methanol in water. Use piston wash and also biocompatible pump, bioinert pump for high salt or high pH mobile phases. Most pump seals, specialized pump seal may be needed for pumps to go above pH 10. Some of these detail is documented in this white paper, 2017, written by several of my co-authors, including engineer from Agilent, published in 2019. Very often, particularly prevalent in older system, the one that particularly have issue is, in my experience, is water alliance systems, which the air bubble can be trapped in the inlet check valve, typically from the mobile A check valve, because that's generally using the weak solvent with aqueous phases with high water tension, which support the formation of bubble. Now, this bubble, when trapped between the check valve, the bore, and the check valve seats, would cause erratic pressure changes. So, air bubble in pump A in the check valve is a very common problem in some pump design, particularly with water alliances. A normal pressure fluctuation when pumps operating normally is pressure below 1% to 3%. When the bubble is trapped in when the check valve, you have very erratic behavior, giving you cavitation. So we mentioned that this is common in water alliance quad pump. That would cause very noisy baseline. So it should be the air bubble should be expelled by first you should wet prime the pump at high flow rate using the aqueous mobile phase. If it does not get rid of the bubble, you should change the solvent to acetonitrile, and that usually would do that. If that does not work, then you have to go a little bit stronger using isopropanol, which is a better wetting agent. And if that doesn't work, then you have to think about changing the check valve. The check valve might be plugged. It might not be functioning properly. So in the water alliance, the check valve is a cartridge, and you should install it with the arrows upward. The operation takes about 15 minutes on first trial, and with practice, you can do it in 5 to 10 minutes. So it's a pretty straightforward operation, and then should resume the wet priming. Here is a list of HPLC column SOP, standard operating procedure. First, if unused columns should be capped and should be capped in methanol water rather than acetonitrile water, also with a plug. Note that the normal pH range for a C18 column or a reverse column is pH 2 to 4 for any silica-based column. Above a pH of 8, silica might dissolve the network, and below 2, some of the bond phase can be hydrolyzed by acid. So this is the proper range. Now, there are some columns which have more extended pH range, for example, hybrid, which support pH from 1 to 12, but this is rated only at room temperature. Column performance typically decreases with age. Normal lifetime is 3 to 12, 24 months with normal sample injection, typically maybe 1,000 to 3,000 injection. If you have dirty samples, should be cleaned up. A dirty sample such as a serum or a plasma sample should be cleaned up. And one should typically would use the gut column for those applications. Eventually, pressure will build up. One should not wait until the pressure build up and when the column become plugged. One should try to remediate it by backflushing the column at low flow rate when the pressure increases by up to 10%. Should do it immediately. Most column can be backflush without issues. Always flush the column with strong solvent before use to prevent lay eluders coming out from the column. Don't let buffer sit inside a pump or a column because it can precipitate out and do damage. So you should rinse it out typically with 10% methanol and water. Continuing on columns connection and use. We're talking about fittings. Note that stainless steel 316 compressional nuts, such as Swagelock, these nuts are 1/16 of an inch, and ferrule are used for internal fluidic connections inside the pump or inside the system. However, for the column connection, one should use finger-tight fittings. One can get very simple fitting for HPLC connection, which support up to 5,000 psi. For UHPLC column, similar fitting should be used from IDEX or optimized fitting. We talk about that a little later. And that should be used for column inlet only. For the outlet only, you can use inexpensive HPLC fitting is sufficient. Note that PEEK fittings and PEEK tubing are not compatible with THF or DMSO. So you have to use stainless steel tubing or stainless steel fittings. When you make a connection, either a finger tight or a wrench connection, make sure that the tubing actually bottoms out inside the fitting before securing or tightening the nut or finger tightening nut. So make sure that's bottomed out. Otherwise, one would have a void in the fitting, and that would be extra column band broadening. Connection tubing for HPLC, PEEK tubing are very useful and very easy to cut. Occasionally, one can also use stainless steel tubing, but make sure that anything in the sample fluidics, where the sample would see it, the inner diameter should be small to prevent extra column band broadening. So typically, the OD is always 1/16 of an inch, and the inner diameter or ID should be from 3,000 to 7,000 inch ID. If you have Agilent system, Agilent actually support this type of capillary tubing shown here, which is with an outer diameter of 1/32. However, the end of the tubing are braced with the 1/16 inch so that to make it compatible with typical HPLC or UHPLC fitting. So these have to be purchased pre-made in that fashion and come with the nuts, or you can change it into finger tight if you want. These type of capillary tubing have different labels. Green stands for a larger ID column, which is 0.17 millimeter, and the black one are much smaller, which have higher back pressure, also if it's long length. Remember that the best fitting for HPLC application below 5,000 psi is the Upchurch PEEK fitting shown here. They're very inexpensive, very useful. The ferrule are one piece built in. UHPLC, one can purchase fitting which are just as good, can seal up to 20,000 psi. However, these are much more expensive. For some of these discussions, this white paper published in 2014 called 7 Common Faux Pas talks about these type of fittings. Okay, we mentioned that do not use these stainless steel fittings such as swage lock for column connection because they don't seal for many times, typically maybe less than 5 or 6 times, and they are not convenient to use because different type of fitting. So there's swage lock over here, which are similar to Parker type of fitting. Valco also make a fitting which have different insertion depth, and Waters have their own fitting, different depth and different shape of the ferrule. So there are different types. So the best way to avoid it in column connection is to use the finger tight resealable fitting, which is the most convenient. Here's the list of my favorite recommended UHPLC fitting. There may be some newer ones available. The one that I recommend are the optimized EXP2 and actually also the IDEX Upchurch. Upchurch, which was acquired by IDEX a decade ago, and these finger tie are probably the best way to go. Dynex, which belongs to Thermo Fisher Scientific, also make a fitting called the Dynex Viper, which is pretty good. However, they don't use ferrules and they use kind of a flange tubing, right? So each of these tubing must be purchased. I mentioned about the best fitting for HPLC below 5,000 psi is this Upchurch one-piece fitting, and also it's recommended to use it on the outlet of a UHPLC column. Next slide, we summarize the auto sampler SOP, mentioning that the split loop type of auto sampler, split loop or integrated loop, is considered the best design with the best performance in terms of precision and also carryover. The best white paper is this paper published in 2019, written mostly by Carsten Paul of Thermo Fisher Scientific. He's a product manager for auto sampler. So this one talk about auto sampler, perspective, principle, practices, the best practices to use on that. A very pretty detailed paper with a lot of discussion, different type of auto sampler. Now there's a type which is perhaps a little bit less popular. It's called the XYZ type, and they require different type of flush solvents. Okay, for example, using Acuity Classics, they require 2 types of purging fluids, okay, shown here, and using an injection mode typically called Pluno, Pluno. But any integrated or split loop auto sampler do not need a flushing solvent, which is quite helpful. Now, any auto sampler which have an external syringe, such as Waters Alliance or Acuity Classics, one must be careful to remove any air bubble in the sampling syringe. If you have an air bubble, you will not pass the precision specification. You will not pass system stability. Typically, for any high sensitivity trace analysis, one need to rinse out the needle, the outside of the needle. It's called a needle wash operation. You can dip the sampling needle in a wash vial, one of the vial reserved for washing, or you can use it in a rinsing station. Now, if you use a rinsing station, make sure you have a rinsing solvent, which is primed by the peristaltic pump. Very important for reminder for any QC operation, for very precise operation, regulated testing, the range for HPLC operation methods is 5 microliter to 100 microliter. Anything below 5 microliter, the precision might be compromised, right? So definitely do not go below 2 microliter for HPLC methods. For UHPLC, typically you inject a smaller volume, typically 1 microliter to 20 microliter. So definitely be careful not to go below 1 microliter because it would be not very precise when you try to aliquot a very sample aliquot. It's much easier to inject 20 microliter or 10 microliter. Any autosampler would do a good job. Also make sure that you understand the loop size of the autosampler, right? So if you have to inject a legacy HPLC method using a larger injection volume, such as 50 microliter, some of the UHPLC might not be able to support it because of insufficiently large loop size. If you have sample where stability could be an issue, then the temperature control of the autosampler sample compartment would be important, right? So some of the autosampler, there's an optional Peltier cooling devices can lower the temperature down to 4 degrees. You cannot go to 0 because of the danger of water being freezing. Carryover could be a problem, particularly in bioanalytical assays. And sometimes you can use pre-column, post-column injection flushes to clean the syringe, also clean the outside of the sampling needle. Some sample might be very sticky to the rotor seal. Some basic drugs would be very sticky and have higher than expected carryover. Some protein are very sticky. So in those cases, you might consider changing a regular rotor seal in the autosampler, which is typically made from polyamide, to either PEEK or Tef cell for sample absorption. Also, polyamide is not compatible at high pH. Above 10, if you do an ion exchange, make sure that the autosampler valve seal is compatible above pH 10. I won't comment too much on this table. This is documented in the white paper. I just mentioned that really pay attention to all the solvent needed in the auto sampling, right? It's a different type of auto sampling for different purposes, for the flushing solvent, for the injector rinsing, different type. There's many different type. Also, pay attention to the sample diluent, the final diluent. Try to avoid a very strong diluent because if you inject a large volume, you might distort the peak, right? So you would get a peak distortion or anomaly when your diluent of the sample is much stronger than the initial starting solvent strength of your method. That's why I want to comment on a study which was done quite a while ago on a older autosampler, which is the XYZ type or the push looped type of autosampler. In those days, typically the precision is not as great as some of the modern autosampler. But one thing that is very distinctive is that any autosampler can inject 20 microliter. You can see that even for this older one, the precision for 10 injection is around 0.1, which is excellent. Down to 10 microliter is also less than 0.2, which is excellent. However, when you try to inject using this type of autosampler down to 2 microliter, then you can see that the precision degrades. Now, this is to be expected because the sampling is using a external sample syringe and using a stepper motor, right? So common sense tell you that the stepper motor have only a certain type of resolution down to perhaps 0.01 microliter. So when you try to inject 1 microliter, you can do it. You can even inject 0.1 microliter, but the precision would not be good. It's very difficult to precisely aliquot 0.1 microliter unless you're using something called a full loop injection. So making a small injection is problematic even for very modern autosampler. Going down below 1 microliter is generally not recommended for QC operation. Now this is a different situation here, right? So this slide, we actually do a study. In this case, we are injecting the same 10 microliter. So volumetrically, they are extremely precise. However, the sample is decreasing in concentration, right? So for the low sample, actually the injection is close to the signal-to-noise ratio of about 10, which is the limit of quantification. You can see that when you inject a very small trace peak near the detection, near the quantification limit, or LOQ, with a signal-to-noise ratio of 10, the precision of that peak area is actually not controlled by the volumetric precision of the autosampler, but it's being controlled by the noise, the integration, how you have a lot of noise, and every time you integrate peaks like this, you have imprecision. Typically at LOQ, the type of precision that the best you can do is about 5 to 10%, and being verified here. This is actually published in today's chemistry work by an ACS journal, which is currently defunct in 2000. The SOP for a UV detector, UV vis detector, and photodiode detector. Uh, the reader or the attendee is really advised to, for more detail, to look at this white paper, which published in LCGC magazine, and you can download it by doing a Google search on that. It gives you a full detail on the best practice on the SOP, on photodiode detectors, and the design and everything. So typically, we leave the detector on and turn off the lamp to save lamp time, because the deuterium lamp using in these detectors are very expensive, typically $1,000 to $2,000. So you don't want to keep it on all the time, right? You want to, but you want to warm it up 15 minutes before you do the assay. You will set the wavelength using your software on the CDA, and also make sure you set the response time correctly. A typical response time for HPLC is 0.1 to 2 seconds, depending on the peak width. I would say at least 5 to 10 points per second. You should get at least 10 points across your narrowest peak. Some of the photodiode detector PDA allow you to change the bandwidth, or allow you to bunch it. So the best standard bandwidth, spectral bandwidth, is about 4 nanometer. Some of the Agilent allow you to tune down the slit width to give you a better spectrum, spectral resolution. However, at 1 nanometer slit width, things are much more noisier, so it's really not recommended. If you have faster peaks in UHPLC, make sure that your detector response time is commensurate with the peak width of the eluting peak. Now, typically, we avoid absorbance over 1.5 AU absorbance unit for the main peak when you're trying to do a stability indicating assay. And the API peak, the active pharmaceutical ingredient peak, is your main peak. Definitely try to, the main peak should not be saturating. Definitely it should not be over 2 when it's near saturation, and when you try to validate the method, you might fail linearity validation. So this is important because typically we are doing something called area underneath the curve, right? Once it's saturated, then the area underneath the curve would not be valid. Typically, we would set the monitoring wavelength to the lambda max of the main component or the API for pharmaceutical analysis. If it does not work, the next um, preferences is in the far UV, perhaps around 210 to 230 nanometer. Lamps have a lamp life 1,000 to 2,000 hours, which sounds like a lot, but it's not. And if you leave it on, it's about 3 months. Typically, it's replaced during annual preventive maintenance every year. So shut down the pump, the lamp, but not the detector when idle. The typical flow cell volume for HPLC is 8 to 10 microliter for HPLC detector and 0.5 to 1 microliter for UHPLC detector. Typical path length is 10 millimeter or 1 centimeter. One can purchase extended path length UHPLC cell anywhere from 25 to 80 millimeter, depending from the vendor. Here is the Agilent HPLC flow cell made from stainless steel. And here is Agilent UHPLC flow cartridge. The flow cell actually is made from a coated silica inside. And the white paper is published in 2019. Just a comparison of noise comparison between new and aged lamp, right? So a new lamp, you expect a noise level around plus or minus 1 or 2 times 10 to the minus 5 AU absorbance unit. When the lamp was used for a long time, it become aged. The intensity of the light is diminished, and you can see that it become much more noisier. This example case study is the effect of UV detector filter constant or the response time, and also the sampling rate from your CDS on the peak width and on column efficiency for fast eluding peak. If you're doing UHPLC with a very quick gradient, 1 or 2 ballistic gradient, or isochronically a very quick eluding peak, make sure that your filter constant response time of the UV detector is commensurate, and your sampling rate can support that. If you don't do that, according to this paper published in 2009, one can get band broadening. You get much lower plate counts and much wider peak width if your filter response time or your sampling rate is not correct. This lists the HPLC system shutdown terminology and procedure. Right? Turn off the column first. Let the column cool down before turning off the pump flow. Flush any buffer or mobile phase out of the system with. You should not use water. Water will support bacterial growth or algae growth. So if you flush out, you should use 10% methanol. Would be a safe solvent to flush out. And turn off the UV lamp, but leave the detector on if you can. For high sensitivity gradient analysis, if you're doing trace analysis, at the end of the sequence, it's a good practice to inject a blank, particularly if you injected a reference standard at the end. Before you shut off, inject a blank and do a full gradient to clean out any of the API or any of the main component adhering to the injector seal or adhering to any part of the system. Here are some guidelines for improving retention time precision. So obviously you need to use a very precise pump and column oven, right? Column oven to thermostat the column is always require, actually is mandatory for automated and precise analysis. For anytime you do anything precise, use a good pump and also thermostat in the column oven. Now most column oven are only heaters only, right? So you need to go above the ambient temperature. Some column oven, which are more expensive, would have a cooling, Peltier cooling function, several $1,000s more. So by default, the standard temperature is 30 degrees centigrade or 35. So this is the standard HPLC. Most HPLC method thermostat at these standard temperature. Generally, you can go up for pharmaceutical analysis. We rarely go above 60 degree. Some protein peptide operation can go to 80 degree, but beware of on-column degradation if you go too high. Pump blending is definitely recommended even for isocratic analysis, for convenience and for method flexibility. Anytime you begin the assay, make sure that you have a stable baseline under UV. Observe the baseline first. Every time you do gradient analysis, definitely you need to equilibrate the column with at least 3 times to 5 times the column void volume. Before you start the sample sequence. Here are some guidelines for improving peak area precision. Number 1, use a precise autosampler. Okay, so the minimum for a QC application is less than 0.5% RSD, even though that a lot of system suitability according to USP is 2%. 2% is not realistic. It's not good. So definitely make sure that it would support less than 0.5. Modern autosampler should be able to do it without a lot of problems down to 0.2% RSD. So autosampler definitely getting better. For precise injection for QC application, a minimum injection volume is 5 microliter. For UHPLC, minimum is 1 microliter. For older autosampler, you need to purge out any air bubble in the sampling syringe. We mentioned split loop or integrated loop autosampler are preferred for higher precision. Now this is probably most practitioners know that in HPLC we not crimped a silicone scepter like in headspace or like GC. We're not doing gas chromatography. If you do that, there could be a problem when you try to withdraw a large amount of sample over 10 microliter because you can create a partial vacuum, right? So definitely using a very loose fitting septum on the sample vial. Some autosampler, such as what is UPLC Classics, require a pre-slit septum, a very thin membrane, a Teflon membrane. Now, obviously, if you inject a very small, low concentration sample near the noise level or near LOQ, do not expect very high precision, right? So make sure the signal-noise ratio of any peaks, if possible, is above 50. The ratio should be above 50 to get very precise injection. Obviously, for a trace impurity peak, that might not be possible. And sampling rate, the support at least 10 to 20 points per peak. When you do integration, it is a good idea to look at the chromatogram at expanded scale and make sure that you actually draw the baseline. You want to know how the CDA, the chromatography data set, CDS, I'm sorry, draw out the baseline. So I have it drawn out. And also try to use some of the more advanced integration algorithm using Apex track. Do not try to do manual integration, which is a red flag for regulatory agency. If you have complex chromatogram, Apex tracks from Empower algorithm for integration is recommended. Here are some guidelines on performing trace analysis using HPLC with UV detection. Use a high POD reagent. Particularly pay attention to the mobile phase A. Rinse all the glassware, including the solvent reservoir, first. If it's contaminated, it would be a big problem. You always run a procedural blank, and make sure there's not any interferences before you do your regulated sample. One can enhance the sensitivity of the HPLC method by UV by selecting the correct detection wavelength. Typically, that's done near the lambda max of the analytes, the main component. Or if that's not possible, you use a 210 to 230 nanometer. If the UV spectrum is on the sloping line, it is definitely okay. Now, do not be concerned about using a detection wavelength at the sloping side of the UV spectrum. It does not make any difference. To increase sensitivity, you can either do two things, using a larger injection volumes or increasing the sample concentration, right? So these are part of the method development, the fine-tuning towards the end. If you're doing external standardization and you want to increase sensitivity, such as a cleaning verification study using UV, one can use an extended path length flow cell to increase UV sensitivity. However, for normal operation, for POD assay, that really do not help because you can saturate the detector very easily with your main component. Often when you use TFA or when you use formic acid and you're trying to using a monitoring wavelength at the far UV 210 to 230, you have a gradient shift, and it's typically procedure to use a balanced absorbance mobile phase, which is using a smaller amount of your additive, such as TFA, the lower percentage from the acetonitrile side of the mobile phase B side, to kind of make sure that the gradient shift is minimum. We talked about that in a prior video. We won't explain that in too much detail. This is the analytical test flow of a regulated analysis or operation under external regulations such as GMP, and the role played by the CDS, the chromatography data system in analytical testing. So these are captured in a very excellent white paper written mostly by Bob Massaris, formerly with Waters, and published in 2010. This is a very general paper on CDS, chromatography data system. So we divided the workflow in three different major segments. First one is sample and reference preparation, which everybody go to, which might include sampling, right? And preparation of your sample, your reference standard, and your mobile phase preparation, and also document everything in a laboratory notebook. And then you transport the sample, you load it into a sample tray into your HPLC, or it could be a GC or IC, and you perform analytical testing. And a lot of these are done by the CDS using instrumental method to set up the instrument. Typically having a method to do a single point connection and control, right? So the CDS can do everything, control all the module, including, and also you load up the sample calibration, the sample sequence setup. You start the sequence. You typically watch the sequence for a while. You do some real-time monitoring for the first few injections, and make sure everything's working properly before you leave the system on autopilot. And then typically we would do a batch processing the next day in a batch. So that includes integration, calibration, make sure the system stability testing is okay, and also evaluating all the sample, and then do the reporting using a reporting method. And eventually these data would get into a result and eventually into a LIMS system of CFA, standing for a certificate of analysis, and for a QA release of the sample. A brief comment on the qualitative analysis strategy. In HPLC using UV detector, really you the only mean to identify uh, your peaks are using a matching retention time, right? So you use a sample, match it to a reference standard. And when you do for early drug development, where if you don't have a standard, we typically identify any unknown peak using a relative retention time indexed to the main component, right? So use relative retention time of the main component is given a 1.00. You can also spike your sample with known analytes for peak confirmation. But the best way is use a mass spec compatible method and use a single quad mass spec to really verify your peak ID. That's the best way. For peak ID and peak identification and POD assessment, one can use PDA, but it's really not very useful PDA POD assessment. Mass spec is give you a more definitive identification either by eyeballing or just looking at the max spectrum. You can perhaps identify any impurity hidden underneath a big peak down to about 1%. Very briefly on the quantitative analysis strategy, we divide it into the three typical standardization method, right? A very popular one is the normalized area percentage method. For during early development phase 1 and early phase 2 methods, typically a normalized area percentage method is assumed to be estimated to be equal to the weight percentage of your sample, which is the gold standard, right? But in the early stage, when things are not, you don't have a lot of reference data, this is allowable and understandable by the regulatory agency. So the area percentage of each peak is reported, is called the HPLC area percentage underneath the curve. And it's almost a taken equivalent to weight percentage. Next is external standardization method. This is used for in your CFA for your potency method when you have a qualified reference standard and you weigh out both the standard and your sample, and then you do a comparative to area percentage. So typically one would use bracketed standard to ensure accuracy. Probably, I would say that probably is, even though everybody do it, it's probably not needed in today's auto sampler when you can get 0.2% RSD, right? For older, so this is still a standard practice, particularly for dissolution method. Occasionally, one use internal standardization method, very popular for bioanalytical method, using a internal standard which is isotopically labeled, such as a deuterated analyte for the API, to do that. Mass spec need that type of standardization because you can get sample loss during the sample preparation, so that we control for that. And also you have ionic suppression in the mass spec, right? So definitely for quantification, you do need isotopically labeled internal standard. Here's a case study on Waterson Power 3, which is a modern, very popular, very common CDS used for both instrumental control and real-time display of both UV and mass spec data. So one of the increasing trend on CDS is that some of the chromatographic data system can also handle simple mass specs such as single quad mass spec, right? Most vendor can support that. So here is the chromatogram in UV in the monitoring wavelength. Here is the real-time mass spectrum on the fly. And this is also the tick file, the total ion chromatogram. Kind of look alike the UV, pretty similar to the UV profile. Here is you have the control part. The green light means that the module is okay. If you have a red light, then you have to take care of the problem. Red light means that there's some problem in there. And here are some of the real-time chromatogram 2 channels, and also including the mass spec and also the status of your sample sequence. Once again, here is also a data table. This is once again a Waters and Power 3 data table. So here we have the chromatogram, which are automatically annotated and labeled. This is really nice. Now in Empower 3, if you have one of the QDA, this system is running with a QDA, which is simple single mass spec, and there's a button called or mass analysis button. Right? Once you press that, something magical happen where you can port over the parent some of the mass spectrum automatically onto the chromatogram. So it's very, very helpful. It will also annotate your lambda max, right? So this is kind of small in there. And if you look at it carefully, one can see that there's label of the lambda max, label of the parent peak from the mass spec, right, which is great for identification. We mentioned something called the Apex track, which is very helpful for very complex chromatogram, right? So instead of the traditional integration algorithm where you have to define a threshold, the upslope threshold and the downslope threshold, the Apex track actually can do it automatically for very complex. So definitely this make much more sense for particularly for emerging peaks. We won't comment too much on the Waters and Power because it took probably several weeks or a couple months for one to be trained. This is the workflow on the Empower sequence, and some of you are familiar with that. You have to create a instrumental method, and then a instrumental method set, a sample set, and a sequence method, and a processing method set. So it's pretty detailed. So you go from the raw data. After integration, calibration, quantitation, you get a result file, and that eventually, with the right report, become a actual report, which eventually can wind up in a released QC data in the form of a certificate of analysis. Now here is an example, once again, of Waters and Power 3 on system suitability tests. Actually, reporting of resolutions, precision, and actually the precision is less than 0.1%, and plate count and signal noise ratio. So all these can be captured very easily onto a data on your CDS on Empower. So here's my summary, HPLC operation. Some of the legacy pumps require wet priming and dry priming. Make sure pump pulsation is good, particularly on the Waters Alliance, making sure that there's no bubble trap in the inlet check valve. Make sure the baseline is stable, definitely less than 5 times 10 to the minus fifth AU. Perform system stability, analyze all the sample in this whole sequence, process it usually the next day over, report the data on the CDS. And definitely when you shut down, you can automate that in the sequence. Rinse the column, shut down the pump, the oven, and the lamp. Here's the set of references. The first one is highly recommended, chapter 4 and 7 of this book over here. There's also a handbook published in 2005. There's some chapter on sample preparation, and some of the white paper on the pump operation, auto sampler, UV detector, and CDS. Here's the end of the video, and we describe episode on 21 HPLC operation, some of the best practices and standard operating procedure for most all the major module. Also some of the strategy for qualitative and quantitative analysis, uh, including how to increase precision for retention time and also for peak area retention. So once again, please subscribe to the channel on YouTube if you are interested in other video coming before or coming after. This is episode 21. We thank LCGC as our channel collaborator. On that note, see you next time, and thank you.